So in the today's topic, our focus will be on the quick sort, which is the second sorting method under the divide and conquer strategy. This sorting approach is also using the recursive functions as it comes under the divide and conquer strategy. And the logic which it follows is that it uses a technique which is known as partitioning. We are finding the array which is given to us, which we have to sort. Okay, we take one element which we call as the pivot, and we find the position of that pivot in the array in such a manner that every element which is greater than that pivot should be on its right side, and every element which is less than that pivot element should be on the left side. Quick quick sort by name, it's not so quick. I mean, if you only look towards its name, it seems to be like that this sorting algorithm will be the quickest among all the sorting. It does not justify that statement. The only thing by which its name has been kept as quick is that the logic which it follows. It's like if we ask the students in the class to arrange themselves in the sorting order. So the one who is tallest among you, he knows that I am the most tallest among all the class. So he will automatically keep himself at the last position in the array, or maybe in the ascending order. So similarly, the smallest one among you, he knows himself that I am the smallest and where my position is. Then the between elements which are present in between the smallest and largest, they will sort themselves based upon their heights or based upon their respective sizes. And you see some examples I have given here, starting with the first array 10, 80, 90. So I have highlighted this 10 here to justify the statement that in this array, in this sorted list which is given here, if we see the element number 10, which is highlighted by some another color, means that this element among whole of this list is in sorted order. Why? Because every element which is present on its right hand side is greater than this element. So we can say that yes, this element is in sorted order. It has been given the sorted position. Similarly, look towards this next one. If we see that this element number 9, is in the sorted order because every element which is lesser than this is on its left side. So if we look towards the third array, here you see the same element, that's 10, is in sorted order. Why? Because all the elements which are greater than this one are on its right side, and all the elements which are smaller than this particular element are on its left side. So the 10 is in the sorted position. So similarly, we then apply the recursive quick sort on the elements on its left side and the recursive quick sort on elements on its right side, because it is a divide and conquer algorithm. So this is the third one I have mentioned it here. This is the actual logic. We divide or we partition the array into two subarrays. And how we do that partition? We find the position of this element in such a manner that every element on its left side should be smaller and all the elements on its right should be greater than this. And this element we call as pivot. And this technique of dividing the left hand side and right hand side of the pivot element in such a manner that right hand side are greater than this pivot is known as partitioning. And partitioning is the main logic which has been followed by the quick sort. So by looking to this example which is given here, you see we are having an array of 8 elements from 10 to 5, and we assign an index I to the first element, that's element number 0, which is equal to 10. And we assign j to this last element, which we assume as infinity, the last one. In the coming slide, it will come to know why. So the first element that's at location number 0, which we have assigned it as I, we take it as the pivot. Okay, so the first element in this particular array is our pivot. Now we have to find its position in such a manner that its left hand side elements will be smaller than this and its right hand elements will be. So in addition to it, we are also assigning this a of 0 as an index L and this last one as an index J, H. So that means this I is also pointing to 10, this L is also pointing to 10. Similarly, both those indices are pointing to the last one of the array. And this will also get visible in the next coming slides why we take two references to the same memory location. So in the next one, the partitioning procedure, what it says? It says that increment I, that is from this side, we have to start from this side. Keep on incrementing this I, which was initially pointing to memory location 0, which is holding 10. So keep on incrementing this I until find element which is greater than pivot. Okay, so keep on incrementing this I. So I was initially 0, it will become plus plus 1, and keep on incrementing until this element is greater than this pivot, which we took the first element. So if we see in this particular case, when we incremented this I, it became 1 and a of 1 is equal to 16. So 16 is greater than this pivot, a of 0. And the next step of this partitioning procedure is that decrement j until find element which is less than pivot. So we are moving in two directions, from this direction, from left to right and from right to left. So I we use to trace this array from going from left to right, and j we use to do the vice versa. So until we find an element from this direction, right to left, which is lower than this 10 pivot, we keep on incrementing the j. Suppose j initially was 9. Since this infinity is not less than 10, so we increment it. It will go or decrement it. It will go to 8. And we compare 5 with 10. Since this 5 is less than 10, so we will reach, our j will reach to here. Okay. So this is the partitioning procedure. And once this two conditions, the two statements above, once those satisfy, we interchange the positions of I and j. Now, to look for these statements in a graphical manner, this example, this whole array, we take here. So what happens is that pivot is the first element. This is the array I had taken. So initially, I will get incremented, I plus plus. Okay. And when it reaches to I plus plus, means I is now pointing to this memory location 1. And what is present inside this memory location? 16. So 16 is greater than 10. Yes. Find element which is greater than pivot. Yes, 16 is greater than 10. So my I is now here at memory location 1. Similarly, going to the next statement, decrement j until find element less than pivot. So I decrement the j by 1. So from 9 it will reach to 8. 9 minus 1 will be equal to 8. And I compare the element which is present at memory location 8, that is 5. Is it less than 10? Yes. If it would have been not less than 10, so I would have decremented j again until I will find an element which is less than this pivot. Since in this particular example, when I incremented I and decrement j by only one, I have been able to get both of these conditions satisfied. So when both of these conditions are satisfied, I had to interchange I and j. The elements which are at memory location I and the element which is at memory location j. So I will do swap a of I will keep it equal to a of j. That means this 5 which was present here, it will come at I location. And this 16 which was present here, it will go to j location. This will be the first pass. So going into the loop again, my I was now pointing to this memory location 1 because it has reached to 1. It will get incremented by 1 more, so it will reach to 2. Compare this second element with 10. Is it greater than? No. So increment I 1 more. I will reach to 3. What is present inside 3? 12. Is 12 greater than 10? That is pivot. Yes. So I will remember this I which is now pointing to 3. So in the same way from j, decrement by 1. So from 8 it will reach to 7. So whatever the element is present at memory 7, that is 9. Is it less than this pivot? Yes. So now j will be pointing to 7 and I will be pointing to 3. Both the conditions are met interchange. So this 3 was containing 12 and this A7 was containing 9. Interchange being 9 here, that's why the swapped or interchanged elements are highlighted in the yellow color. So this 9 will come here, this 12 will go here. Okay, second iteration. Now the third one. Now my I is now, it will get incremented to 4. This element, what is present inside 4? 15. Is it greater than 10, this pivot? Yes. And from the jth side, it will go to 3. That is memory location 6. Is it less than 10? Yes. 3 and 15 will be exchanged or swapped. So the 3 will come here in this and this 15 will go there. It is clear here. So now I is pointing to memory location 4 and j is pointing to memory location 6 until we have completed third iteration. The loop will again start and I will get incremented again. So I will now go to 5. Is 6 greater than 10? No. I will get incremented again. It will reach to here. In this, you see, I have now pointed to 6, which is containing 15. So this condition is true. Coming to the j was pointing to 66, which was containing 15. So it will get decremented. It will now point to 5. Okay. When it points to 5, which contains 6, that is less than this. But we have to stop this procedure until we reach I greater than j. So if I becomes greater than j, here you see I is now 6, j is now 5. To stop the loop here. Okay. And whatever the j is pointing to, the memory location to which this j will be pointing when we stop this loop, that will be the position of this pivot. That means our pivot was a of 0 containing 10. Now the last statement in our loop is j is equal to 5, which contains 6. So swap those because this a of j will be the position of the pivot. Very important point. So 6 will come here and this 10 will go there. And its color is in red to highlight that this is the pivot position. Now, if we see this final array which we got after these set of iterations, this is just like this array. What we found is that we found the position of pivot, and every element on the left hand side of this pivot is lesser than pivot, and every element which is greater than this pivot is on the right hand side. So if we see this array, only one element is sorted, that's 10. And remaining left hand side array is not sorted, this is not sorted. Because 12 should have then come here. And similarly, this 3 would have come on the first. So only this element is sorted. So we have partitioned this array into two sub-arrays. This original array, we have partitioned in two arrays using the partitioning procedure. And we found the position of the pivot such that every element on its right hand side is greater than it and every element on its left hand side is lesser than, and both those subarrays are not sorted. Go for the recursive quicksort on both the arrays. That's the logic of divide and conquer. So this is the actual quicksort recursive algorithm, the divide and conquer. So I will take this example here, this, where I have initialized this I to the first memory location A of 0. L is also assigned to A of 0. And this J and H are assigned to the last memory location. Pivot is the first one. Now see here. So we will firstly look to the partition because we are initially doing the partitioning, which is the actual logic behind the quicksort. And then we will go to the quicksort divide and conquer algorithm. So there are two functions we can say in our terminology. The first one is the partition, and we are passing two arguments to it. The first and the last, L and H, pointing to the first element, pointing to the last. So pivot, we take the first element, A of L, A of 0, because L is pointing to 0, that indicates the same thing. Pivot is the first. And I, we are pointing again to first. J, we are pointing to H. Whatever H is pointing, J is also pointing to the same thing initially. Then we go and we forget about this while we go inside this. What we do is that we first of all do I plus plus. So we start from the left hand side of the loop. And this I plus plus will go until A of I will be either equal to pivot or less than, which means in other terms, pivot is greater than this A of I. This is what we have been seeing from the left hand side. And similarly, keep on doing J minus minus, that start from right hand side and decrement this J index at each iteration until you find an element A of J which is greater than pivot. And if I is less than J, the condition where you find that I becomes less than J. So at that very time, swap those two elements. Bring A of J into A of I's position and take A of I into A of J position. And this condition, this iteration or for loop or looping should repeat, keep on repeating until and unless I is less than J. Once this condition becomes false, J becomes greater than, I becomes greater than J, exit this loop, and you have found the position of the pivot element. That pivot, as we have taken the first element, A of L. A of L is pointing to 0. So in other terms, A of L is again the pivot element, the first 0th location element. And A of J is the position of the pivot. So swap those. Bring A of J and take A of 1 into A of J. And return the Jth location, means the return the position of the pivot. So this way, this partitioning is giving us this result. Because this is this first one, which was pivot, it is A of L. This has become our A of J. We swap those and we are getting the position of the pivot. So now the actual quicksort. Again, we are passing it the arguments from L to H, beginning to end, and until this condition becomes true, that L is less than H. So what we do, we invoke this partitioning algorithm. So this partitioning algorithm will give us this result. This partitioning algorithm will give this result. And then we go for quick sort. We recursively call quick sort from L to J. J is the location which contains this position of this pivot. So we take this left subarray and invoke quicksort on it, and we take quicksort from J plus 1. J plus 1 means from here to this H, to this H. And this way, each and every time, we find the exact location of every element in such a manner that all the elements on its right will be greater than, all the elements on its left will be less than. And finally, the whole array will be sorted in this manner. Example that we are having 15 elements in an array from 1, 2, 3, 4 to 15. So we are assuming one thing, that partitioning is always done in the middle. Partitioning is always done in the middle, which means initially what we will be passing to this quicksort or the partitioning algorithm will be this L, which is the first element, and the last H, which is 15, 1 comma 15. So when we assume that partitioning is done in the middle, which means in the next iteration, we are passing the array from this to this and from this to that, excluding this sorted because it is already sorted. So that's why when we assume that partitioning is done in middle, so middle means 1 plus 15 divided by 2. So that will become 8. So we assume that this 8 is already sorted. So now, when the quicksort will be called for the remaining unsorted elements, so there will be two arrays. One will be from 1 to 7, the next will be from 9 to 15 on right hand side. So since we are again assuming that partitioning is done in the middle each time, so in this subarray 1, 7, the middle will be 4. We are assuming that to be sorted. So it will be again divided into two subarrays from 1 to 3 and 5 to 7. Yes, same will be done on right side. Here we are passing 9 to 15 and its middle element will be 12. So 12 will be sorted again from 9 to 11 and 13 to 15 quick sort will be invoked. Finally, when we are having this 1 to 3, we find its mid value 3 plus 1 divided by 2, that will be 2. That is sorted or partitioning is done in that element. So the left hand side array will be again divided into two subarrays 1 to 1, 3 to 3. Because here I and J will be pointing to the same memory location. That's this what is, or L and H, where we are actually passing to this quick sort. When we reach to 1 element array, L is equal to H at that very time. That's why you see both the subscripts of the same value. So what the first thing is that here in this pass, that is the first pass, we are having n elements from 1 to 15, 15 elements, or from n elements means n elements if we are having an array of n size. And if we see here in this pass, that is the second one, we are having the elements from 1 to 7 and 9 to 15, which means n minus 1. Because 8 we are assuming we have found its position, it is sorted. So here it will be 15 minus 1 or 16 minus 1 or 15 minus 1, whatever is. So it is n minus 1, but we assume it also equal to n because we are trying to find out the formula which is a general one. Similarly, here in this part, 1 to 3, 5 to 7, this is sorted, this is sorted, this is sorted, this is sorted. So we again take it n minus, it will become n minus 4. But we take it for the sake of convenience n because in that way our problem will not be able to come to a final value. So what we are doing is that initially we are having these n elements for general formula and we keep on dividing into two arrays. It was initially one, it was then two arrays, it was again then two, two, this is divided two, this is divided two, then this is divided two. So we actually do n two times we keep on dividing. And how many times we keep on dividing until this n by 2 by 2 by 2 becomes equal to 1 finally. Because we should be able to get one array at the last extreme step. So in the same way we did it for merge sort, this will become n by 2 to the power k. That should be equal to 1 finally. And n will reach equal to 2 to the power k, and we get the k equal to log n levels. So if we had to find again the number of levels the quick sort will be using to sort this array of size 16 or 15, we will directly put the value log n, log 15, that will be k is equal to 4. So it is 1, 2, 3, and 4. You getting? And time complexity is again equal to number of levels which I have found here log n into the number of the total elements in this array, that's n log n. Its time complexity is similar as the time complexity of the merge sort. So this is not quicker than that. Even the merge sort displays the same complexity in the best case. Now, suppose this is an array and this list of numbers is already in sorted order. 2, 4, 8, 10, this is already in sorted order. And I am invoking the quick sort on this list. So what it will do when it takes this first element as pivot, the first element will be taken as pivot. Okay, the list is already sorted, so initially we are having n elements from this location to that 1 to 7. Then in the next iteration, when it takes this as pivot, that's element number first, which we took also in the example, and what it will find its location. And when it takes all of those steps in between, and finally it returns j to us, which means the location of this pivot. And since here all the elements which are present on the right hand side of this pivot are greater than it, so its location will be again returned the same thing. Okay, so we have found initially we have passed the array size from 1 to 7. Now in the next iteration, since its location is found, we will go to I plus plus, that's 4. We will try to find out its sorted location. And when we invoke the quick sort whole logic on this element so as to find, we will again return back to this same location. Because it is already sorted, but quick sort does not know it is in sorted order. It will invoke the logic which it follows, it will invoke this on this array. This is we people who know that this is sorted. So in the same way, in the next iteration, we will be passing from element number 2 to element number 7. Okay, and it will now do n minus 1 comparisons or n minus 1 because it has to compare it with all the elements so as to find its exact position. Here it has to do n, here it has to do n minus 1, or we are passing n minus 1 elements here, n minus 1 here, because one element is decreased. Similarly, we go to the next iteration. We are passing now. We have found its position also. We now try to find the position of this element, invoking recursive quicksort. So we are passing n minus 2 elements now. 7 minus 2, 5 elements, 1, 2, 3, 4, 5. So in the same way, when we reach to here, we will be passing only 2 elements. Now in this step, it will try to find out the position of 18 and return back, it will give the same position. Finally, we will be passing it one element, which is 17. Okay, it should be here. Okay, this 17 should be here. There is some minor error. This 17 should be here. 18 should be here, because this isn't sorted as I took example. This is a typo. So finally, we reach to 7, 7 means we are passing this. We are passing the 18th 7th element, which is 18. So it will return back its original memory location. That's why it is time complexity will be then 1, because this is the only element which will be left. So if I find out the total time complexity it will be the sum of these different number of time it will take in different steps. 1 plus 2 plus n minus 1 plus n minus 1 plus n. And that's equal to how much? N into n minus 1 by 2. The sum of the first n integer numbers. And when we found, that's equal to order of n square, because n will get multiplied to n. And this is the biggest problem with this algorithm, that its worst case time complexity comes out to be order of n square. So quick is not quick. By the name, quick never is a quick algorithm. The best case is comparable to the other sorting algorithms, but the worst, it has the exponential quadratic time complexity, and that also comes when the list is already sorted. So on a sorted array, the quicksort performs very less for order of quadratic time. Now the problem arises where? The problem arises from this thing, that's the pivot element. Whatever the element we take as pivot, that is actually where the problem rises. And if we had to do some improvements in the quicksort algorithm for the worst case, best case is manageable. For the worst case, if we had to do some improvements, we do two things. Either we select middle element as pivot, that is this element, we find the mid value of the original array and we found the mid value. Okay, and we take that mid as the partitioning position or pivot, because when we take from here, we have to traverse whole of the array from n, then to n minus 1 elements, then to n minus 2, then to n minus 3. This way, some improvements could be possible in the quicksort. And the second one is that we take any random element as pivot. Any random element can be taken as pivot, not necessary that always this first element will be taken as pivot. So in this case, it has given good results because this is a sort of random picking of the pivot element. The array is not sorted, so we can take any one. We have taken the first one just for the purpose of simplicity. But if we always keep on taking the first one and our array will be like this, the quicksort will take, its performance will degrade. So the best solution is to take a pivot element, any one, whatever is suitable. Make habit either to take it as a middle one or take any element at a random. Because quicksort will not be able to understand the list is in sorted order. Even if it is sorted and we take any middle element, That way, the improvement could be possible in the quick sort. Now, we will go to another, forget about this Tower of Hanoi we will discuss in today's topic also, because this is also an algorithm which comes under the divide and conquer strategy. This is also a divide and conquer algorithm. That's what I am focusing. And the problem is that we are having some disk here given, disk, the number of disks 2, 3, n, which are inside a pole type of, it is a pole here. So the disks are arranged in their decreasing order of size. The element which will be present at the bottom of this pole will be the biggest disk, then smaller one, then smaller, then smaller, and smaller. Suppose this is a pole A, okay? So the problem of Hanoi says that we have to shift all those disks from this A to this C tower, taking help of this middle tower, which is known as auxiliary tower, in such a manner that at a particular time, no smaller disk should come at the bottom and larger disk will come at top. So the condition or constraint to be maintained is this thing. The smaller one should never come lower to the bigger one. And we will now try to find how it could be solved, is that since it is a divide and conquer strategy, so we will take its small problem and big problem. So initially we will take just one disk. The disk is in tower A and we have to move it to tower C, and it's a small problem for us. Then we will go to the big problem by using the logic of the small problem. So when we are having a single disk, we just use this instruction to move it from A to C. At that point, the intermediate or auxiliary tower B is not used. Now, getting a little bit bigger, we take two disks, 1 and 2. Here the constraint is maintained. There's 2 which is smaller is present at top of 1. Now we have to move both of those disks to here, but this positioning or arrangement of the disk had to be maintained. So what we will do is that move a disk from A to B using C. This is the very important statement. You see, when we are having only one disk, we directly use a statement move from A to C. When we take the intermediate tower also into our work, we use the statement which is this sort of. So move a disk from A to B. Take one disk. So since it is a stack type of data structure, only we can take the data from this end. So when we use this instruction, move a disk from A to B, take the topmost disk and keep it in B using C, which means that C will be also used at this point. And if we go now to the next step, in the previous step, we have taken 2 from A to B using C. So this 2, the top disk has come here. Now we are left with disk 1 disk only. So we will use the next statement, move a disk from A to C. Now we are directly shifting the disk from A to C without using this B. Because here the solution we have to find is between A and C. Mark the difference between those instructions. So now 1 is here, 2 is here. So the third one step will be simply that we take a disk from B, that is this one, to C, that is this one, using E. So we take this disk which was present at tower B and we keep it at top of this one in tower C. So we have been able to find a solution for 2 disks also. So Let's go a little bit bigger. Take 3 disks. In the original tower, the disk arrangement is maintained. The smallest is at the top, middle, and then the largest. So we use the same terminology. That is this one. Initially, we take the top disk, which was present at the top of this A. Means we move a disk from A to B using C. So the disk which is present at top, we take it from A to B. We will write the same statement in case of 3 disks. That is, move disk from A to B using C. The same statement. The only condition is that we take those 2 disks at a single time. Not at a single time, because only one disk we take at a time, but whatever is at the top of this disk 1, which is the bigger one, we write it as equal. We have to firstly take this 3, okay, then we have to keep this 2 here, because if we take this 3 into B and take this 2 also on the top of this 3, the condition will get violated, because 3 is smaller, 2 will become on the top of that. So that's why we are using C, means we are using the tower C also here. We will take this 3 into C, then we will take this 2 into B, then we will bring it back into B on the top. So 2 is at the bottom, 3 will be at the top. Then we will go for this one. So any element which is any number of disks at the top of this large disk, we will be using this statement, and that recursively will do arrange the disk in their respective orders. See what happens here. Move 2 disks from A to B using C, A to B using C. This is what we did. So our arrangement will be like this when we use only this statement. Move 2 disks from A to B using C. So the top, any number of top most disk will be arranged in those 2 towers, that is tower B and C, by this statement. And then only one disk is left in tower A. So top and disks are moved from this tower to the remaining 2 towers in the order which is the initial condition, that largest will come at the bottom. Now we are having only one big disk here, so we will move a disk from A to C. That disk we take from A and keep it in C, which is the largest one. So this was the same statement if you see for two disk problem. Move a disk from A to C. So this statement is same. Only thing is that we take all those n disk from this tower A to B and C using this statement. Then there will be only one disk left here, that is the biggest one. Then we will shift it directly to A to C. And that's what we do here. We move 2 disks from A to B, that's topmost 2 using C. We move from A to B using the C also as an intermediate. Then we are having only one disk left here, which is the largest one. We shift it from A to C directly. Then the third step is that move 2 disks from B to C. The remaining 2, we will move them from B to C because we have to shift it to tower C. But if we shift it like this, that 3 will come, then 2 will come, that will be wrong. That's why we are using the A tower in here. When we are using 2 towers, we use this type of syntax. So what it will do, move 2 disks from B to C, but use also the intermediate tower A. So that means that it will take firstly this 3 here, then it will take 2 on the top of this, then it will take A from this to top of C, and the arrangement will be again maintained. So we cite for 1, for 2, for 3, and this is the general formula. Now we will generalize the statements for AND disk problem. That is the actual solution. If it works only for this guy, that's not a solution. Solution is that which always works for the general public, for the general society, and we take the AND disk problem. That's the actual tower of Hanoi. So we will not do anything new. The only thing is that when we were having 3 disks here, 3, we take 3 minus 1 from A to B using C. That's that number of disk here minus 1. Then we take only 1 disk from A to C. Then we take again n minus 1, that's 2 from B to C using A. When 3, it was 2. So when it is n, we will take n minus 1 from A to B using C, from A to B using C. We are not changing anything, we are generalizing it for n statement, n disk. Then move a disk from A to C, that is similar. Then again move n minus 1. Move n minus 1 disk from B to C using A, from B to C using A. All right, this is the actual divide and conquer algorithm for the Tower of Hanoi. The 3 statements, these are the same here, and this is the pseudocode. So what we are passing to this Tower of Hanoi algorithm is the number of disks n, tower A, B, and C. And we are saying that if n is greater than 0, definitely it should be. So make a recursive call to Tower of Hanoi again, but passing argument n minus 1, n minus 1. A, C, and B. This is tower A, this is tower C, tower B. And match the sequence of this A, C, B with this statement. When we are using C tower as an intermediate, it is coming in the middle. So we are shifting from A to B in this step, using C as middle in the first, in this recursive call. So whatever the tower is in the middle, that we are using as intermediate. So the next step is that move only 1 disk from A to C. Move a disk from this to A to C, means we are moving A to C 1 disk. Okay, since it is just 1, it's a small problem, so there will be no n involved. Then we again call this Tower of Hanoi by passing again argument n minus 1, but now we are passing from, shifting from B to C, from B to C using A as intermediate. That's why A comes in the middle. I have pointed the arrows here, which means we use those towers like in this sequence. And since here we are then shifting A to C, means we are shifting all the disks into the tower C. And that was the actual goal which we were to do. So let's trace this algorithm for 3 disks. That's this problem. Let's see it's working. It's very interesting. So according to this pseudocode, what we will be sending initially, that is the first recursive call. First call actually, Tower of Hanoi. We will be passing n as the number of disks to it, which is equal to 3. Okay. So this is the index of towers 3, 1, 2, 3. 1 will stand for A, 2 will stand for B, and this C will stand for, 3 will stand for C. That's what we are initially passing. So now the actual recursive call begins. First of all, it will call recursively Tower of Hanoi again, Tower of Hanoi, but it will do n minus 1. So initially it was 3 disks, now it's 2. Okay, and the sequence will get changed. A, C, B, A, C, B. A is represented by 1, 1. C is represented by 3, so that's why 3 came in the middle. And 2 represents B, that comes at the back. So we are actually shifting from A to B using C, the first statement. Now the printf, that is the statement number 2 from the pseudocode. What it will do? It will simply shift a disk from A to C, from A to C. So A is our what? 1. and C is our 3. So it will shift a disk from 1 to 3, tower 1 to tower 3, A to C. So that since this is not a recursive call, it will print. It will give us a step that do this step, shift from 1 to 3. And again, a recursive call will be made here in this level. Tower of Hanoi, n minus 1 will be again 2. Now it is BAC. B is for 2, 2. A is for 1, 1. C is for 3, 3. The order of the towers. So this we have got. Now this is a recursive call, this is a recursive call. They will in turn again go for recursive again, because this is still a big problem, divided into small chunks. So this one that is on the left hand side, leave it for some time. Let's go to left hand side. Tower of Hanoi. So what it will do, it will again call itself Tower of Hanoi by decrementing its parameter one more. From 2 it will become 1. The remaining thing it will become from A, C, B. Since now this is equal to 1, A, this is equal to B, this is equal to C. So this will be A, 1, C, this will be 2, and this will be B, which is equal to 3. Okay. So similarly, now in this direction, the printf statement, the shift will take from tower 1 to 2. That is from tower A to C. A is 1 and tower C is our 2 here in this now recursive call. 1, 3, 2 we are passing now. So C becomes our 2. So this becomes our small problem. So this becomes on the right hand side again, it again invokes itself by decrementing its parameter 1 and using this sequence of towers, BAC. All right. So I won't go into such a detail. You can have a look on it. So finally, we will be dividing this whole problem into small little problems. Because when this 1 will become equal to 0, the condition will fail. So we have got the very small. So this will then finally, when it becomes equal to 1, it will print 1 to 3. So 1 to 3 means just shift the disk from tower 1, that's A, to C. So this will be the first pass. It will print and when it becomes small. This 1, 2 is this next. This will give 3, 2. This will give 1, 3. This will give 2, 1. This will give 2, 3. This is 1 give 1, 3. So the Tower of Hanoi algorithm says me that for 3 disks or even for n disk, follow this sequence of steps automatically. Let's follow. This is the sequence of 3 disks 1, 2, 3. So the first step is that use 1 to 3. So that means shift the disk from tower 1 to 3. Okay, this is the first shifting. So let's shift. So 3 will shift to this tower. So 3 has shifted to here. The remaining are these 1, 2. So the next step is shift 1 to 2. So shift 1 to 2, which means that 2 will come here, the topmost. Okay. Now the remaining one is shift 3 to 2. Make a shift from 3 to 2. The 3 will come at top of 2.